Hello, welcome. Welcome to Learning Unit 6, which is about strengthening mechanisms. We learned in previous learning units that the movement of dislocations is responsible for plastic deformation. Around a dislocation, we have what are called strain fields. So if we look at the edge, the bottom edge of the edge dislocation, we can see that due to the inserted layer above, there is, because something's being squashed in there when there ordinarily wouldn't be, there is compressive strains in the green region, and below it, below the edge dislocation, because something was inserted, because a half plane was inserted into the crystal, the yellow region gets stretched, and so is in tension. So because there is a strain and there is an energy associated with the presence of the dislocation. When two dislocations interact, the strain fields around them interact and can cause repulsion, where that occurs when like strain fields, for instance a compressive strain field starts to interact with another compressive strain field, or they can actually attract each other and annihilate each other if strain fields of opposite type collide. So the reason I'm telling you this is to understand that if we have more than one dislocation in the crystal and these dislocations move close to each other, they can attract or repel each other. So the dislocations interact with each other. Another interesting way in which a crystal can deform is by twinning. So imagine we have a crystal here. This is a polished surface. If we apply a shear stress, so the left side is being pulled down and the right side being pushed up, what will happen is that we can get a kink forming in the crystal. So if we follow this line here, the crystal kinks down to here and then carries back how it was before. So what we have now are what are called twins, and we have twin boundaries here where we have a kink in the crystal and then here it kinks back to what it was before. And under a microscope, these twins appear as thick parallel lines. You can see twinning in this brass specimen. And in fact, if you go to Santa Monica Pier, close to Bubba Gump's, I believe, there is a bronze dolphin. And if you look at it closely, the weathering has revealed the crystal grains in the bronze, and you'll be able to see twinning in the crystals. So take a look next time you're out there. So we've learned that dislocations can interact, they can repel each other, and we've learned about this mechanism of twinning. Now, how can we strengthen materials? Well, we can strengthen materials by preventing dislocations from moving. And we're going to look at some ways in which dislocations can be impeded in their movement. Something that we discussed in previous chapters was grain size reduction. Reducing the size of the grains increases the number of grain boundaries in materials, and the dislocations find it very hard to move over a grain boundary because of the disruption in the crystal order at the grain boundary. And so the more grain boundaries we have, we can increase strength in this way. And we can see that in this diagram. The scale here is the reciprocal of the square root of the diameter of the grains. So that means that as the diameter increases, this value, the reciprocal of the square root, decreases. So over here, let me just get my pen working. So in this region, this represents large crystals, and here small crystals in the polycrystalline structure. So we can see that as the grain size reduces, we get increase in yield strength. And if you remember, you'd plotted a graph like this in one of the homework problems, and you applied what is called the Hall-Petch equation, which gives the relationship between how yield strength changes with the average diameter, average grain size. Another way in which we can impede dislocations is to introduce foreign atoms. If we introduce foreign atoms, we can, and the two materials are fully what we call miscible, which means they mix in any proportion, we will get a solid solution. Here we see nickel content in copper. As the nickel content increases from 10, 20, 30, 40, 50%, we see the yield strength of the material increasing. But this strength comes at the cost of ductility. As we increase nickel content, we see that the elongation reduces, hence the ductility is reducing. So we can increase strength at the expense of ductility. The solid solution strengthening increases strength by disrupting the crystal lattice, and which impedes the movement of dislocations. Another technique another mechanism that results in impeding the movement of dislocations is called strain hardening. What happens when a material is strained is that the dislocation density in the material increases greatly. There become so many dislocations that they start interfering with each other's movement, and the material is strengthened. Let's have a look at this graph. This shows a material that has been stretched, or has been loaded and stretched, and then unloaded, and then put back in the machine. Upon reloading, we find that the yield point has increased. The material has got stronger. It takes more force now to cause the material to yield than it did before. That is because during the initial plastic deformation, a large number of dislocations were produced. These dislocations now, when the material is loaded again, prevent the slipping of planes in the prevent the movement of dislocation of the material, which means that a higher stress level is required to cause plastic deformation. If we repeat the cycle where we unload and return, we see that the yield strength keeps on increasing until the material gets very hard, but also brittle, and you see that it fails in a non-ductile manner with increased amount of cycling in this case. You can show this practically if you get a piece of copper, for instance a copper tube. When it's if you've ever done plumbing with a copper tube, you can get copper coils of copper. Once you get it and try and straighten it out to do some plumbing somewhere, if we try and bend it after it's been unbent or rolled out, it becomes harder actually to straighten out, and that's because of this phenomenon of strain hardening. So you see the copper hardening. The more times you bend it, the harder it becomes to straighten out. So I want to show you a few operations, some cold forming operations. So these are operations where the material undergoes a change of shape at a relatively low temperature. I hope you enjoyed watching those videos of the cold forming processes. I want to now talk about the strain hardening exponent. For metals, the relationship between the true stress and strain in the plastic portion, this is where the material is starting to yield, is of this form. So you can see that we have, this is the what's known as the true stress, the force divided by the actual cross-sectional area. And that's equal to K multiplied by the true strain to the power N. So the power N here, let me just highlight that for you. Right there. N is the strain hardening exponent, and which lies between the values of 0 and 1. 0 means the material is perfectly plastic, and 1 means the material is perfectly elastic. If we look at the graphs of stress versus strain, sorry about the quality of the image, for 0 strain hardening exponents, we see the stress versus strain graph is flat, meaning that the material just continues to yield. At n equals 1, it's linear. Okay, stress is equal. Stress is a linear function. Sorry, the strain is a linear function of the applied stress. In between, we get these curves. The strain hardening exponent, it can be dependent on the strain rate, and that's known as strain rate sensitivity. So materials that are deformed quickly can harden quickly as well. Materials with a high rate or a high strain rate sensitivity are very good for car bodies, but car body steels, because a lot more energy is absorbed during an impact. And we can see some curves here of different materials for different values of strain rate sensitivity and the strain hardening exponent. I want to talk about a phenomenon called springback. If we bend a piece of metal that is originally straight, and then we bend it to a right angle, as shown in the hatched portion of the diagram, when we let go, when we remove the force, it doesn't remain in that 90-degree position. That is because some of the strain that is created is elastic or recoverable, and the material will spring back, and that's known as springback. If we take a piece of material and we bend it one way and then we bend it back, okay, let's have a look at this. So we bend it one way and then we bend it back, we notice that the yield strength on the backwards portion is less than on the forward loading portion. And that's because of what's called residual stresses created in the material by deforming it. And this effect is called the Bauschinger effect. So how does strain hardening work? Strain hardening works because when we bend a material, we create dislocations. These dislocations start to move, and they may get pinned by pinning sites. They start to bow, and when they bow, they form a loop. And this loop now can radiate out, and another dislocation starts to form in the middle. In this way, one dislocation can produce many dislocations, and this is called a Frank-Reed source. And you can see in the transmission electron micrograph of a Frank-Reed source. I want to show you the video that's at the link here, which animates the Frank-Reed source, or animates the Frank-Reed source. So you can see here dislocation getting pinned, forming loops, and then forming another loops, and the previous loop keeps radiating out. And In this way, the dislocation density increases by many orders of magnitude when a strain is applied to a material. We get so many dislocations that interfere with each other, which hardens the material. I want to talk about a number called the cold work for a prismatic shape. Prismatic means that something that has a constant cross section all the way through its length. So something like a tube or a square section rod is prismatic. We define the cold work as the percentage reduction in cross-sectional area as the material is deformed. So this is the original cross-sectional area. We subtract from that the final cross-sectional area and divide by the original. The percentage cold work for a rolling process or another kind of process like that allows us to determine how much the material has been plastically deformed. A sub 0 always applies to the original state of the material. So if you go through two processes where you successively reduce the diameter, A0 will always be the same number, which is the beginning cross-sectional area of the material. So you may have seen, so let me just sketch here. Perhaps you're wondering, imagine I have a material with a cross-section like so, a square cross-section. I could then put it through a process where the cross-sectional area gets smaller. And here I'll just show the rest of it here. Hopefully you don't mind my drawing too much, but what's happened is that imagine you squeeze the end so the cross-sectional area got less. You could say that the percentage cold work in this area can be calculated according to the above equation. So what happens to the material properties as we increase the percentage cold work? The tensile strength goes up, the yield strength goes up, but however the material gets harder and less ductile, and the percentage elongation goes down. We can use cold work to tailor the mechanical properties of the material to what we desire. First, we may heat treat the material to put it into a standard state, which we will call zero cold work, in an annealed state. If we want to increase the tensile strength, we can cold work it to the appropriate amount to get that final tensile strength. Obviously, we will have to start off with the larger diameter or cross-sectional area, so that when we reduce the cross-sectional area to get the required amount of cold work, we will reduce it to the required shape. Of course, if there's a constraint on the percentage elongation, we have to make sure that we don't cold work too much, otherwise we lose the ductility and may go below specification. So when we cold work, the advantages are the material is shaped and strengthened at the same time. Cold work can produce a fine finish and excellent dimensional tolerance. It's a low-cost technique suitable for high-volume production. The disadvantages are that it leads to an embrittlement of the data under high percentage cold work, and properties such as electrical conductivity and corrosion resistance are impaired. Also, residual stresses remain in the material, which effectively reduce the tensile strength. But there are things that we can do to relieve those stresses. Texture is when the crystals in the material are not orientated randomly, but actually in a preferred direction. And rolling a piece of metal actually produces texturing. And this can be either a good thing or a bad thing. Let's do this problem here to show an example of how we apply the cold work percentage value. It says here that a cylindrical 1040 steel having a minimum tensile strength of 865 megapascals, a ductility of at least 10% elongation, and a final diameter of 6 millimeters is desired. Some 7.94 millimeter diameter 1040 steel stock, which has been cold worked 20%, is available. Describe the procedure you would follow to obtain this material. Assume that 1040 steel experiences cracking at 40% cold work. So the material that we need must have a minimum tensile strength of 865. Let's take a look at our graphs to determine where 865 is. So we're looking at 1040 steel, and we need to have a tensile strength. So tensile strength is here. That's 8, that's 900. So we're just slightly above the halfway mark, drawing a line. So we need to be here, which corresponds to a 30% cold work. 30% cold work is required to get the strength, but we need a ductility of at least 10% elongation. So let's have a look at the ductility. 10%. Can we get 10% at a cold work of 30? Yes, we can. So what we're aiming for is, so we need a cold work percentage of 30%. It's supplied in a 20% form, 20% cold work form, but we have to also make sure that we get the final diameter down to 6 millimeters. So let's do some math to figure out how we can achieve this. So the first thing we're going to do our diameter in the or the radius of the material in the provided form is 8.97 millimeters. So 3.97, do I say 8 point? Because yes, it's 7.94 millimeters diameter. That's the supplied state. So I'll call this R sub S. There we go. We know that this has a cold work percentage of 20%. What I'd like to do now is to find out what the original diameter must have been, or the original radius, and I will call that R sub 0. We can figure out what R sub 0 must have been, and this is the cold work percentage equals 0, by using the equation for cold work. Cold work percentage is equal to the original area minus the final area over the original area. This will equal the original radius squared times pi minus the final radius squared, or in this case it's going to be the supplied state divided by pi r naught squared. Taking out the pi, so we get, let me just erase that. What's going? There we go. So we have r naught squared minus r squared divided by r naught squared. And we know that this is equal to 0.2 in the as supplied state. If we plug in the values that Rs is equal to 3.97 millimeters and solve for R naught, we get R sub naught is equal to 4.44 millimeters. Okay, so now we know what the original diameter of the material was before it was cold work and then supplied. Okay, so the material is supplied at the metal yard in the cold work state. Let's ask ourselves, is it possible to then simply cold work the as supplied material down to the required diameter, which is the required diameter is 3. So let me draw here. If we go straight from R naught, had we gone straight from R naught to RF, okay, where RF equals 3, will we risk cracking the material? So I'm not actually saying that I'm going to unexpand this, but what I've done is calculated what the size of the rod must have been before it was cold work and then supplied. If I attempt to squeeze the supplied material down to 3 millimeters, then the cold work can be calculated using this same equation, but we must remember that A naught will always equal the cross-sectional area of the original material in its non-cold work state. So if we go, if we attempt to cold work from supplied state, to RF equals 3 millimeters, then the percentage cold work is equal to this equation. But remember, this A naught is the original diameter in its on-cold work state. The original area. We don't use this, the cross-sectional area in the supplied state, in this equation when we're calculating the percentage cold work. So what we're going to do here is, I'm going to use this equation. So R naught, we know, is 4.44 squared minus 3 squared divided by 4.44 squared is equal to 0.54, okay, which is 54%. So if we intended to squeeze the material down from its supplied state to 3 millimeters, the material would crack because it's we're cold working more than 40%. And the problem tells us that the material will crack at 40% cold work. So how do we solve this problem? Well, what we're going to do, we're going to cold work down to an intermediate diameter. Then we're going to heat treat it in a process called annealing. The heat treatment step is called annealing. Let's have a look at these graphs here. We have tensile strength, grain size, and elongation. After some percentage cold work, up to say 100 here, we see that the tensile strength goes up and plateaus. The grain size stays constant under cold work, and the elongation goes down. Now, if we take the cold work sample, the 100% cold work sample, and put it in a heater or a heat treatment furnace, we see that at 200 degrees centigrade, or roughly just beyond that, about 300, we see the material properties change rapidly. Just before the precipitous fall here of the tensile strength up to here, this is called right up to there actually, before the grain size drops, that's called recovery. After that point, which is called the recrystallization phase, the tensile strength drops and the elongation increases back up again. So does the grain size. Well, the grain size increases during a period called grain growth. And then you can see after a while, if we get up to 600 degrees centigrade, the material has been returned to its original uncold worked state. So by heating up the material and annealing it, we can return it to its cold work, original 0% cold work state. But remember, the material has changed shape since, so we can shape it, squeeze it, anneal it to return it to a 0% cold work state, which means that the diameter has been reduced, but it no longer has the properties of a cold work material. This allows further cold working, and that's what the annealing step allows you to do. It allows you to keep shaping the material without the material cracking. So let's apply that to this problem. So what we need to do is we realize that in the final diameter, so we know that RF is equal to 3 millimeters. I would like to find RI, which is the intermediate diameter. I know that this will be, let me sketch it out so it's easy for you. So what we're going to do here is we've got the 0% cold work. Then we're going to go down to an intermediate. And then we're going to go down to the final diameter. Which is 3 millimeters. So, but we know that we need to have 30% cold work in this state. So let's try to calculate the diameter of this intermediate step. In between these two steps, we are going to anneal. Okay, and here we're going to cold work. So I know that Ri squared minus RF squared over Ri squared must equal 0.3. So therefore, what I get is that the intermediate diameter must be 3.56 millimeters. After shaping the original material, what I've done actually, what I should have, perhaps it would have been easier to understand if I put in over here RS. RS is a supplied state. So now let's see I put RS. So now we're going to ask, can the supplied material be reduced in diameter down to Ri, which is equal to 3.56 millimeters. Well, what would be the percentage cold work in this state? Where we calculate that is we're going to do R0 squared, because there's no annealing step between these two. We want to eliminate any need for annealing because it wastes time and energy, or it would be a waste of time and energy if we didn't need it. R0 squared minus Ri squared over R0 squared. And when I calculate that out, I get that's equal to 36%. So therefore, yes, what we can do in order to make a material, within the specifications that are required, these are the steps we need to do. So, 1, take supplied material, at 20% cold work, 2, reduce diameter, or I should say radius, Ri, 3, anneal, because this is now at it's now reached 36% cold work at this point. And so here we anneal. We don't know the temperature, don't know the exact material, but we need to do an annealing stage, and at the end of the annealing stage we can consider the material, even though its diameter is reduced, is now being returned to 0% cold work state. So I'm just checking these graphs here. Okay. Sorry about it. I just realized I used the wrong symbol here. 0% cold work. There we go. Then let's reduce the diameter. To RF to result in 30% cold work. We need to have the final material with a percentage cold work to get the increased tensile strength that we want, and the we don't want to over cold work because then we'll miss the specification for the ductility. So that's how you solve that particular problem. We're going to go back to discussing annealing, and we realize that the material properties change drastically at this point here, which is the end of recovery. Between then there's a recrystallization stage. At the end of the recrystallization, the material properties are the grain size has been reduced. You can see that. The tensile strength is slightly above what it used to be, and the elongation is almost returned. If we keep increasing the temperature, we get grain growth. The grain size increases, and the tensile strength should actually start increasing as well. I mean decreasing with the increasing grain size. The recrystallization occurs at a certain temperature. Cold working is when the material is worked below the recrystallization temperature. So that's the definition of what cold means. Let's look at the effect of the microstructure on microstructure of cold working. After deformation, there are a lot of dislocations in the material that are tangled. And that's what these little specks represent. The dark lines represent the boundaries of the crystals, crystal grains in material. After heating above the recrystallization temperature, we get what's called recovery. What recovery is the migration of the dislocations into boundaries. And these boundaries are within the original crystal grains, and this is called a polygonized cell structure. Then after increasing the temperature, we get recrystallization. So this is what happens is that we get grains starting to form within the polygonized cell boundary walls, and which relieves and annihilates the dislocations, hence reducing dislocation density and restoring ductility to the material. With more time and increasing temperature, we get grain growths. So these grains compete, they grow and into one another to increase the average grain size. So let's see that. Let's say an actual piece of brass. I believe this is brass. This is a cold work material, so this will contain a tangle of dislocations. At the beginning of crystallization, we see crystals forming at the, we can't see the polygonized cell wall structure, but they will be forming within the cell walls. We get increased or intermediate recrystallization, and then full recrystallization. After that, we get grain growth, and this is further grain growth. The temperature at which recrystallization occurs is not actually fixed, but it depends upon a number of factors such as the degree of cold working. But we have some figures here for standardized materials, or under presumably standard conditions, to give us a general idea of what the values of the recrystallization temperatures are. What's interesting is that for some materials, such as tin and lead, the recrystallization temperature is below room temperature. So that means that when we're bending a piece of lead at room temperature, the cold working, well, we're actually hot working it, and we're not building up dislocations in the material. This means you can't cold work lead at room temperature, and hence this explains why lead is so pliable. It can be bent back and forth many times without hardening. We see for zinc also the recrystallization temperature is below room temperature. For aluminum, it's above room temperature at 150 degrees centigrade. Note that the recrystallization temperature is well below the melting temperature of the material. When we deform the material at temperatures above the recrystallization temperature, that is called hot working. And dislocation density does not increase during hot working because it is dislocations are immediately removed through recrystallization. And you can have a look at some videos here of hot working techniques. In the hot state, you can deform the material as much as you like, as many times as you want, without hardening the material. And that is an advantage of hot working, in that you can produce very large distortions or strains in the material. The disadvantage is that the high temperatures mean that the surface of the material will be attacked by the environment, leading to oxidation, for instance, and a degradation in finish. During hot working, if the temperature is closely controlled, the elongated grains that are formed during rolling can immediately recrystallize to form a fine grain structure. So hot rolling material not only shapes it, but also strengthens it. We talked about annealing and how that was used. Just moving this, there we go. We talked about annealing and how that was used to return the material, a shaped material, back to its original state so it could be shaped further. In that case, annealing was useful. In some cases, annealing happens when we don't want it to. For instance, let's say we have purchased some cold work steel. We purchased it in that state because we wanted a strengthened steel. If we go and then weld it, the heat created from the welding will cause what's called a heat-affected zone. In that heat-affected zone, the strength of the material may be reduced with respect to the main part of the material, or the unaffected material. So we can see here that where closer to the weld we get grain growth, we have a recrystallization zone as well. So we can have unintended effects when we apply heat to join materials. So that's it for this module. Thank you very much.